Hello, my name is Olivetti. This is a joint work with Sebastian Brandt, and this talk will be on truly tight in delta bounds for bipartite maximal matching and variance. We will prove truly tight lower and upper bounds for maximal matching and some of its variance, meaning that we will prove the exact time complexity of these problems as a function of delta, the degree of the graph. So let's start from maximal matching. We have to find a subset of edges such that each node is incident to at most one edge and such that this set is maximal, meaning that we cannot add additional edges without violating the first constraint. Note that this is a very easy task in the centralized setting that we can solve by using a greedy algorithm. What we study in this work is the distributed complexity of this problem. We will not only consider maximal matching, but we will also consider variance of it. In particular, we consider x-Maximal y matchings that are defined as follows. We want to find a subset of edges such that each node is incident to at most y edges of the set, and such that if a node is not matched and hence not incident to any edge of the set, then at least the minimum between its degree and delta minus x neighbors should be matched. The second constraint, if we think about delta regular graphs, just says that if a node is not matched, then at most x neighbors can be unmatched as well. Note that 0 maximal 1 matching is the standard maximal matching problem. And if we increase x and y, we obtain easier and easier problems. Let's see an example. In the picture, there is an example of 1 maximal 2 matching. In fact, we can note that some nodes are incident to one edge of the matching, some nodes are incident to two edges of the matching, but not more. And nodes that are unmatched satisfy that at most one of their neighbors is also unmatched. In this work, we give tight bounds for the complexity of x-Maximal y matchings. But let's first describe the model that we consider. We are in the local model of distributed computing, hence we consider networks where nodes have unique IDs, nodes can communicate in synchronous rounds, and we do not restrict the size of the messages, nor the amount of computation that nodes can locally perform. In this model, we measure the time complexity as the number of rounds required to solve the task. Note that since we do not restrict the size of the messages and the computation, this is equivalent to give a bound on the distance that nodes have to see in the graph in order to be able to output their part of the solution. In the following, we will restrict the setting a bit, and we will only consider bipartite two-color graphs. Notice that while this makes the upper bounds weaker, this makes the lower bounds stronger, since lower bounds that apply to two-color graphs apply to normal graphs as well. But let's restrict the setting even further and consider the case where nodes do not even have IDs and the graph is delta regular. We also assume that each node has an order assigned to its neighbors, so for example a node can decide to send a specific message to its second neighbor. And in this setting, let's see how we can easily solve maximal matching. Let's see an example in a graph that is 3 regular, where nodes are properly two-colored, and we want nodes to output a matching. In particular, we want each node to know for each incident edge if it is part of the matching or not. And there is a very simple algorithm that solves this problem called the proposal algorithm. The high-level idea is the following. White nodes propose to their black neighbors, one at a time, and black nodes accept one proposal and reject all the others. So at the first round, white nodes start by sending a proposal via their port number 1. Some black nodes may receive just one proposal and they would accept it. Some may receive multiple proposals and some may receive no proposals at all. Nodes that receive multiple proposals just accept one and reject the others. And edges where proposals have been accepted become part of the matching. So this is what the partial solution looks like after one phase of proposals that require 2 rounds in total. Notice that this is a matching, but it is not maximal. For example, the third white node and the last black node are both neighbors and unmatched, so we could extend this matching. So the second phase starts then, where white unmatched nodes propose via their port number 2. In this case, the first node is unlucky and proposes to a node that is already matched, while the third white node is lucky, since it proposed to some unmatched black node that received only one proposal. Hence, the first request will be rejected, while the second will be accepted. And this is what the partial solution looks like after the end of the second phase. Nodes repeat this for each incident edge. So the first white node continues by proposing via its last port. Unfortunately, this neighbor is already matched, so the proposal will be rejected. What we obtained is indeed a maximal matching, so let's see why these algorithms work. First, note that since white nodes propose to one neighbor at a time, and black nodes never accept more than one proposal, the result is a matching. We have to argue that it is maximal. Let's first consider white nodes. If a white node ends up to be unmatched, it means that it proposed to all neighbors, and it got rejected by all of them, meaning that they all accepted some other proposal, and hence that they are all matched. Let's consider now black nodes. If a black node is unmatched, it means that it never received proposals, and it means that all its white neighbors stopped before reaching the phase in which they would have proposed to this black node. But this means that all the white neighbors of such node are already matched. So the matching is indeed maximal. So this is a very simple algorithm that solves maximal matching on bipartite graphs. It requires delta phases of 2 rounds each, so 2 delta rounds in total. Can we do better? No. Last year it has been shown that this algorithm is asymptotically optimal, and thus that maximal matching even on bipartite graphs requires linear in delta rounds of communication. And this is what we know about maximal matching if we move from the simple setting shown before to the more standard local model. Here complexities are represented as f of delta plus g of n. Some existing algorithms have a multiplicative dependency between the two variables, so they have been simplified a bit to be represented in this way. So let's see what we know about maximal matching. Since the 90s, we know that in the usual setting, without a given 2 coloring, the problem cannot be solved with a running time that only depends on delta, and that the dependency on n must be at least log star. Also, since the late 90s, from the upper bound side, we know that even with deterministic algorithms, the problem is solvable in polylog n. So there was a huge gap between known lower and upper bounds as a function of n, and nothing was known about the dependency on delta. Until 2004, when Kuhn et al. Showed a lower bound that holds even for randomized algorithms, that essentially says that maximal matching requires at least log delta over log delta unless we spend at least root log over log as a function of n. And a much more recent result from last year proved a stronger result, showing that sublinear in delta algorithms cannot exist unless we spend some high dependency on n, where by high here we mean log over log for deterministic algorithms and log over log for randomized algorithms. For example, there cannot exist an algorithm running in log star n plus log delta. A first result that we show is the exact complexity of bipartite maximal matching as a function of delta. We show that bipartite maximal matching, we know that bipartite maximal matching requires linear in delta time, and we know that the simple algorithm that we have seen before solves the problem in 2 delta rounds. We show that bipartite maximal matching requires exactly 2 delta minus 1 rounds. So it is actually possible to slightly improve the proposal algorithm by 1 round, and this was already known actually, but we cannot do better. So we proved that 2 delta minus 1 rounds are sufficient and necessary. This implies that this very simple algorithm that we have seen before is not only asymptotically optimal, but this is actually optimal. There is nothing better than proposing to neighbors one by one and at this time wait for their response. We cannot solve maximal matching on bipartite 2-color graphs in 2 delta minus 2 rounds, even if we use much more complicated strategies. This result holds in this simple setting where nodes have no IDs, but we can lift this bound to hold also in the standard local model of distributed computing. what we obtain is that this problem cannot be solved in less than 2 delta minus 1 rounds unless we spend some high dependency on n. Essentially, we get the same as the lower bound of last year, but we improve the dependency in delta. So same lower bound in n, but we improve delta. We get tight bounds for delta. Then we go one step further. We also prove tight bounds for many variants of maximal matching, for which no lower bounds were known before. We proved that in the bipartite setting, the x-Maximal y matching problem requires exactly 2 times the ceiling of delta minus x over y, and that we can shave off 1 round if some condition is satisfied. Recall that x-Maximal y matching means that a node can be matched to other y neighbors, and if it is unmatched, at least delta minus x neighbors need to be matched. In fact, by setting x equal to 0 and y equal to 1, we get maximal matching and a bound of 2 delta minus 1. That is the same that we have seen before. This result essentially says that even relaxed matchings are hard. In fact, if we set x and y equal to some constants, we still get that the time complexity to solve this problem is linear in delta. This implies that it is not possible to just slightly relax maximal matching and get some problem that is much easier. Let's now see how we can actually prove these results. Let's first look at the upper bound. If we just take the proposal algorithm that we have seen before and we generalize it to find x-Maximal y matchings, for example by doing y proposals in parallel instead of just one, and by performing delta minus x over y phases of proposals instead of delta, we get the running time that we want, but we do not get a correct solution. In particular, one can prove that the maximality constraint is only satisfied on one side by black nodes. What we show is a different way to do proposals, where black and white nodes interleave in making proposals that actually gives a correct solution within the required running time. This is anyways a very simple algorithm, and the hard part in proving our results is actually proving the lower bounds. In order to prove our lower bounds, we show that for any x, y, and I, it is possible to define a problem that has a somehow simple description and is exactly I rounds easier than x-Maximal y matching. This gives us a deep understanding of the maximal matching problem and its variants, and this is one of the main contributions of our work. In order to do this, we use the round elimination technique. That is a technique that has been used in the last years to prove interesting lower bounds in the local model, and our results contribute to a better understanding of this technique. So let's see how the round elimination technique works. We start from a problem, P0, for which we want to prove a lower bound of t plus 1 rounds. And we do a proof by contradiction. We assume that we have an algorithm that solves P0 in t rounds, and we show that this assumption would imply that we can define some other problem, P1, that can be solved in t minus 1 rounds. Then we repeat the same reasoning by showing that this statement would imply that we can construct some different problem, P2, that can be solved in t minus 2 rounds. If we repeat this reasoning t times, we get a problem that can be solved in 0 rounds. But if we now prove that this problem cannot actually be solved in 0 rounds, we get a contradiction, implying that P0 cannot be solved in t rounds. So we get a lower bound of t plus 1 for P0. Now, one of the hard parts in applying this technique is to come up with a family of problems, P1, P2, and so on, up to Pt, that satisfies these constraints. That is, for each problem Pi plus 1 is at least 1 round easier. Fortunately for us, a result of last year showed that this process of finding such a family can actually be automated, if the problem is locally checkable, meaning that it can be described by local constraints. Such technique can be used to find a problem that is exactly 1 round easier than the given problem. Unfortunately, if we just apply such a technique, we may get a family of problems where at each step we have a problem whose description is exponentially larger than the problem of the step before. Hence, if we want to use this technique in practice, we need to find a way to simplify the intermediate problems that we obtain and keep their description small, while still respecting this constraint of being at least one round easier than the previous problem. The hard part in doing that is to simplify problems without making them too easy, actually, since we want to repeat this procedure as many times as possible. Note that this is not a new technique. In fact, the lower bound of Linial for 3 coloring cycles can be seen as an application of the round elimination technique. This proof essentially shows that if C coloring can be solved in T rounds, then there is some problem that can be solved slightly faster, in at most T-1 rounds, that is 2 to the C coloring. If we now recursively apply this reasoning, by starting from a value of T that is too small, that is Lidl of log star n, then we get that Lidl of n coloring can be solved in 0 rounds. That we can show to be a contradiction. As said before, in order to apply the round elimination technique, we need to be able to describe a problem by just defining some local constraints. So let's see how we can do this for maximal matching in such a way that we can indeed apply round elimination. The idea is the following. We require white nodes to output one label for each incident edge, and we list all possible allowed black and white configurations that are multi-sets of size delta that describe what are good labelings around each node. And we are interested in the time required for white nodes to produce a correct solution. For example, we allow white nodes to either output M as matched on one incident edge and O on all the others, or output P on all incident edges. P stands for pointer, and the idea is that if a white node is unmatched, it must point to only matched black nodes. Hence, black nodes having an incident edge labeled M can accept both P or O on the other edges, while if they do not have any edge labeled M, they cannot accept P's, meaning that all edges must be labeled O. So, we can describe maximal matching in a formal and compact way by just giving these two regular expressions, and in the picture we can see an example of a labeling that encodes a maximal matching and satisfies the constraints. Now, before seeing how we can prove our results, it is helpful to see the high-level idea behind the linear in delta lower bound that has been proved last year. The idea is the following. The first step is to prove that if maximal matching can be solved fast, then a variant of matching, that is zero maximal root delta matching, can be solved even faster. More in detail, a sublinear in delta algorithm for the first problem implies a sub-root delta algorithm for the second one. Then, the round elimination technique is applied by showing that there exists a sequence of problems Pi, such that P0 is the zero maximal root delta matching, Pi plus 1 is at least one round easier than Pi, and that P Lidl of root delta cannot be solved in 0 rounds, implying that zero maximal root delta matching cannot be solved in Lidl of root delta rounds, and thus implying that maximal matching cannot be solved in sub-linear in delta rounds. So this is the high-level idea, but let us now see more in detail this second part, the one that uses round elimination. In particular, let us see the reason why we cannot directly start from maximal matching, but we need to pass through this intermediate problem, zero maximal root delta matching. So we start from zero maximal root delta matching and apply the round elimination technique of Sebastian, and thus automatically obtain some problem P1. Now we cannot just repeat this process starting from P1, because unfortunately the size of the description of these problems would grow really fast, and thus it becomes harder and harder to compute such problems. So instead, what is done is to take P1 and simplify its description complexity. The main challenge here is that this must be done very carefully. We must start from P1 and somehow modify its constraints such that the obtained problem P1 prime is still at least one round easier than P0, while being much smaller to describe than P1. If we do this, we can repeat this process from P1 prime, obtain P2, perform some new simplifications, obtain P2 prime, and so on. The authors show that there are some simplifications that can be done that satisfy these requirements, and that simplify each intermediate problem and make it quite small. In particular, each intermediate problem Pi prime can be described by using just 4 labels. And recall that maximal matching can be described using 3 labels. So the exponential growth in the description complexity can be avoided. Unfortunately, if we start from maximal matching, by doing such simplifications, we cannot repeat this process a number of times that is linear in delta. Because after just root delta steps, we get a problem that is 0 round solvable, meaning that the simplifications that are done to each intermediate problem are too severe. And this approach would only give a root delta lower bound for maximal matching. Fortunately, if instead of starting from maximal matching, we start from 0 maximal root delta matching, we can still perform the same root delta rounds before getting to a 0 round solvable problem. Meaning that for this variant of matching, these simplifications are actually good enough. So let us see what we do in our work now. We heavily simplify the original maximal matching lower bound proof. In fact, we followed the same approach, but now we directly start from the problem of interest and not some variant of it. For example, for proving a lower bound for 2 maximal 3 matching, we really start from 2 maximal 3 matching and not some more relaxed version. The thing that we do differently is the simplification part. We found better simplifications that we can perform to each intermediate problem, such that in order to get to a 0 round solvable problem, we really have to perform T steps, where T is the true complexity of the problem. This implies that we are able to reduce the description complexity of some problem Pi and obtain Pi prime, and what we get is that Pi and Pi prime have the exact same complexity, so we don't lose anything. And we can perform such simplifications such that each intermediate problem Pi prime can be described with just 5 labels. So if we just allow 1 label more, we can do much better. Recall that the lower bound of last year used 4 labels. Hence, we now know that for every x, y, and I, we can describe in a very compact way, using just constraints over 5 labels, a problem that is exactly I rounds easier than x-Maximal y matching. Now, the bounds that we get only work for the port numbering model, and the reason is that the automatic round elimination technique does not directly work if we consider unique IDs. But we can nevertheless lift such bounds to the local model, using standard techniques. The idea is that we can first convert our bound to a randomized lower bound for the port numbering model, and then argue that with randomness, we can generate unique IDs with high probability, and hence obtaining a randomized lower bound for the local model. Finally, we can show that a good randomized lower bound implies an even better deterministic lower bound by just using known results in the complexity landscape of locally checkable problems. So let's recap what we have seen. For any possible variant of x-Maximal y matching, and for any I, we are able to define a problem that is exactly I rounds easier than x-Maximal y matching. And such a problem can be even described shortly by just using 5 labels. And this gives us a deep understanding on the maximal matching problem and variants, because this essentially tells us what should be the intermediate problem that we should be able to solve at each step if at the end we want to find a matching. And of course, this implies that we know the exact complexity of these problems. Our work also helps in better understanding the round elimination technique. We show that in some cases it is possible to avoid the exponential growth in the description of the problems given by the automatic round elimination technique, while still not losing anything in the time complexity. There are some recent results that show lower bounds for ruling sets, where the number of labels is not kept constant, but they grow linearly at each step. And it would be nice to understand if this growth is really needed. Another open question here is to try to better understand the delta plus 1 vertex coloring. A first step would be to at least understand if we can prove or not some bound using round elimination by keeping the number of labels small. And by small I mean linear in delta or quadratic in all intermediate problems. And that's it. Thanks for listening.